fact that I'm trying to build this chart, I think I drew this for you last class. We're gonna try to connect these two classes of compounds together. So we're gonna try to learn how to take an alkane and turn it into a haloalkane. It's really hard. So in an alkane, you only have carbon-carbon bonds and carbon-hydrogen bonds. Carbon-carbon and carbon-hydrogen bonds are both quite strong single bonds, and carbon and hydrogen have almost equal electronegativities, 2.2 and 2.6. So they're really non-polar. So you've got a strong thing that's not polar. So there's not much of a way to change it, like it just wants to be there. And so alkanes will last a long time, but you can burn them quite effectively. So in the presence of oxygen, you can indeed oxidize them. But outside of that, they don't do a lot of chemistry. The only chemistry that we're gonna learn about, other than just burning them, is this process, where we're gonna take an alkane. Do you have like a medium-sized alkane that you'd like me to work with? Do you just want me to guess? Ethane. Here we are, we have ethane. And we are gonna add to it a halogen. I'm gonna choose chlorine. You can choose bromine. I'm gonna try to make loopy L chlorine so that they really look like CLs and they don't look like something else, but sometimes I just marvel at the fact that I write chlorine 3 different ways on the board and think about it. So I'm gonna do my best. And in the presence of UV light, if you don't write this, you don't get the mark. It makes a haloalkane and hydrogen chloride. Now Emma is wondering why we call that hydrogen chloride and not hydrochloric acid. The answer is because this is happening in the gas phase. And when we have HCl in the gas phase, we refer to it as hydrogen chloride. We do not refer to it as hydrochloric acid until it's in water.
So all free radical substitution is gas phase.
So you could have bromine here, which is a liquid. So no, but
Just not
the product, I'm just calling it right. Like I'm just defending my choice. It's a pretty gas phasey thing. It's a higher energy thing. Yes?
Is free radical substitution the specific thing of changing an alkane to a haloalkane, or is it just like a general process?
Yes. So the process, this mechanism, is free radical substitution. And I will draw that picture. I will tell you the name of the mechanism is free radical substitution. And I will tell you that the 2 reagents that are necessary are ultraviolet light and some halogen. Again, I refer to all of the things in group 17 as X when I don't care which one I've got. And so X2 is just like a generic halogen. But chlorine and bromine are far and away the most common. Fluorine's very hard to keep in the lab. It's super reactive and dangerous. HF eats glass, so you have to have special glassware to do this because you can't use glass. We don't see fluorine a whole lot. So that is the overall reaction. Again, I'm taking any alkane and I am functionalizing it with the halogen. It's magical, because I'm gonna be able to do chemistry with that. I'm gonna be able to turn that into ethanol. That's good. Laugh later. The way we do that is a 3-step. There are 3 major steps. Within the steps, there are sub-steps. So we got into a little bit of a tussle last time we did this. There are 3 major steps in this. The first step is known as initiation. This is going to start the free radical process. And in initiation, what is going to happen is that in the presence of relatively high energy ultraviolet light, I am going to break chlorine into free radicals. One way of conveying that idea is like that. One more time, if you don't write the UV light, you don't get the mark. On the left-hand side, I have chlorine, the molecule, and on the right-hand side, I balance equations for a living. I have 2 chlorines where I've shown you that they have an odd number of electrons. The presence of this, like, by itself electron is what makes this a radical. They're very reactive. Electrons don't like to be by themselves. This is going to go find something to attack and make some new molecules. If you buy fancy cream at the store like Ethan Morgan, you're going to know that it will talk about preventing your skin from being damaged by free radicals. It absorbs the free radicals. So this is just an example of them. They're super reactive. They would mess with yourselves.
We don't like free.
Another way of drawing this that will also get you the marks, but is more complicated, is to actually consider a little bit more of the structure. So here I am showing you not quite a Lewis structure, but you can draw it as a Lewis structure with a single bond in between the two chlorines. How many electrons are in that single bond? And what I'm going to show you is that the two electrons can become free radicals upon the homolytic cleavage of this bond. Homolytic cleavage. So we're going to break the same way. And what that means here is that there were two electrons. Audrey's going to take one, and I'm going to take one. We are going to share equally. It is homolytic. Most of the reactions that we handle are heterolytic. Audrey's going to take both electrons and leave me with a positive charge. She's going to have a negative charge. This is the only reaction that will have homolytic cleavage. So a very common multiple choice question will rely on your understanding free radical substitution, homolytic, everything else not so. Again, we are breaking the bond to make the radicals, to make the two chlorine dots. Often on the mark scheme, it will say that the dots are not required. I think that's pure garbage. On my mark scheme, it will say you have to draw the dot. You do not have to draw the lone pairs. I'm fine with that. But I don't think you can understand this if you can't see the radical. So it is the UV light that's breaking that bond, and the way it is breaking it is homolytically.
So it's the UV light?
It is the UV light that is doing this. This is the only reaction where we will be using light. It's not a catalyst because it doesn't meet that definition, but we're using light as the impetus for this reaction to take place. Yes, it's in your magic.
So chlorine is,
Yes, it
so
is.
chlorine is the only one that's homolytic?
Free radical substitution reactions always have a halogen. The first step of any free radical substitution reaction is initiation. It will always have UV light breaking a halogen-halogen bond homolytically. Now, do you notice that the arrows I am drawing are one-sided? We call these harpoon arrows. Do you feel that? Back in the days when you guys drew electron configurations of like fluorine, I did it wrong the other day, so don't judge me. Fluorine would be, do you remember the electron configuration of fluorine? Yeah. So I want you to say it's 1s2, 2s2, 2p5. She's trying to tell me I would do this. 5. You see how those are one-sided arrows, harpoon arrows? That's because that represents a single electron. There's another thing I'm a little emotional about. It's in your textbook. I didn't make this up. But a one-sided arrow means one electron is moving. So one electron from this bond is moving to that chlorine. One electron from this bond is moving to this chlorine. No. If this were heterolytic cleavage, we would have both electrons moving to one chlorine. That would result in chlorine having an extra lone pair and a minus charge. That was Audrey. And chlorine missing an electron and having a positive charge. So this is heterolytic.
Does that happen often?
That is going to happen in every mechanism that is not the one we're studying today. So I'm just trying to draw attention to the fact that I'm drawing some goofy arrows. They don't look like normal arrows, but I'm doing it with purpose because it reflects a single electron moving. Every other reaction we do will have two electrons moving, and we'll work through that next week and the week after. So this is coming, but this is the opposite of homolytic. Again, here, each chlorine takes one of the electrons. Heterolytic means we're going to split them differently. One chlorine takes two, the other chlorine has none. Now that we have made radicals, we're going to work on the substitution. Perhaps you can see that in this ethane molecule, the carbons are bonded to 6 hydrogens, and I'm going to substitute one of the hydrogens for a chlorine. So the word substitution means that one of the H's is going to be substituted by a chlorine. And so to do that, the second big step is called propagation. What does propagation mean to you?
I've heard it in biology.
You've heard it in biology. You might
Plants though.
propagate plants. You might propagate genes. So if your parent is a carrier for something, that gene might propagate. Your offspring might be carriers, might not be. So propagation has the notion of making more of something that is the same. Think about the Bible, propagate means make babies.
Really?
Yeah.
Yes.
It's one of the directives. You have to go out and make babies.
I mean, there are only 2 of them.
It's a rule, right? Go forth and multiply.
Yeah.
The first one is be fruitful.
Okay. So propagation, what we're going to do is we're going to take the chlorine radical that we just made, and we are going to react it with our halogen, which I'm now drawing out a little bit more carefully. So this should look like ethane. That's why I asked you for something that was kind of not too big. And in this step, what's going to go down is we are going to make a bond and break a bond. The bond we are going to make is going to be between this very reactive chlorine and this hydrogen that we are stealing. The fancy chemistry word for stealing is abstracting. We are abstracting a hydrogen from the ethane. And then this electron that used to be in the carbon-hydrogen single bond is going to end up as a radical on that carbon. So the products are going to be hydrogen chloride. I'm going to write it in the same order so maybe it makes more sense. And the ethyl radical. So in propagation, what you will notice is that we have one radical on the left side and one radical on the right side. So part of this radical reaction will be that each step has to keep a radical in the box, in the reactant container, so that we can keep doing this complicated new chemistry. Yes?
Can you go over again how like the abstraction?
The chlorine swims up to this hydrogen and is like, hey man, let's make a bond. And so the hydrogen lets go of the carbon.
Like more attraction or something, like why?
Honestly, I would think that this is a weaker bond than that. I would guess that delta H here is not super good.
Something new.
It's a fair question. The next bond we make is going to be a stronger bond, and so I imagine that my answer is going to be that the badness of this is offset by the goodness of the next thing. Like the badness of this class is offset by the glory of lunch. Next up, the ethyl radical is going to do some business. The ethyl radical is going to find a chlorine molecule and it's going to do the same kind of thing. It's going to be like, hey, sweet, sweet chlorine, let's make a bond. That is going to leave behind a chlorine radical. These 2 steps are going to make propagation. We're going to discuss why that is in a second. So I'm going to draw the products. I was left with a chlorine radical and chloroethane. So we term this propagation because we started this chain with a chlorine radical, and we ended up with a new chlorine radical that is ready to find another ethane to keep reacting. So we turn on that light for just a minute to make a few chlorine radicals, but once we have those radicals present, they will start a chain reaction, reacting with all of the ethanes because this reaction regenerates or propagates them. In propagation, there are 2 steps, and what I notice about each of them is they have a radical on the left and a radical on the right. One more thing I want to notice about propagation is I'd like to try to add these two equations together. And I know they got kind of busy, so you're going to have to do this a little bit in your head. But when we add two chemical equations together, we treat it like algebra, and we cancel out the things that appear on both sides. And so my chlorine cloud and my chlorine cloud are going to cancel. My ethyl radical and my ethyl radical are going to cancel. And I'm going to be left with ethane and chlorine making hydrogen chloride and chloroethane. I don't like how I'm writing it, so I'm going to stop. That is our overall chemical reaction. So this is where the reaction is occurring. We made an intermediate, the chlorine dot, in that first step. It allowed us to make the intermediate ethyl radical. The ethyl radical allowed us to recreate that chlorine dot. This is the chemistry. But sometimes bad things happen and the pathway dies. And so the third step here, again, the third big step, is known as termination.
It's like initiation.
It is just like that. In termination, there are no colons on the others, so let's get rid of that. What happens is that two radicals find each other. Try to be consistent with my arrow drawing. I'm going to draw the two radicals in different directions. But if two chlorine radicals were to find each other and my light is not on, the two radicals could form that sigma bond, make chlorine, and this would stop the propagation, right? These two chlorine radicals would be dead to us. They could not engage in propagation. And DT would have to turn on the light again to break this bond again. Another thing that could happen is a chlorine radical could come up to an ethyl radical. And the product there would be honestly what we're trying to make. But it would kill this chlorine radical. It would prevent more from reacting. No, we would get 1 unit of our chloroethane. And a little bit surprisingly, 2 of these ethyls could come together. And they could make a bond. End up with C4H10. Most likely it would look like butane. But I've run out of room and cares. In a typical question, if they asked you about this, they would ask you for an initiation step. If you don't write the UV light, you don't get the mark, but the arrows are optional. They would ask you for 2 steps about propagation. And they would ask you for a single termination, so you can kind of pick your favorite of these 3. In initiation, we have no radicals becoming 2. So 0 on the left, 2 on the right. In propagation, we have 1 on the left, 1 on the right. And in termination, we have 2 on the left, 0 on the right. There's like a pattern. It helps you not do things that are silly. It's the worst day ever? Now there's some downsides to this reaction mechanism. The question is, if Luke were to put propane into a reaction flask, what would he get out? if Luke were to put propane into this reaction flask instead of ethane, what would he get out? That was an extra carbon, I'll take it. Okay? So, I'll write the HCl, and Carthen's treating this like it's obvious, which I appreciate. But what I was hoping you would see without the hydrogens, that the chlorine could attack in two positions. The chlorine could be in the center 2 ways, and the chlorine could be on the edge 6 ways. So you might expect that there's a 3-to-1 distribution between a 1 chloropropane and a 2 chloropropane. But you also might find that the chlorine has a hard time getting to the inside of this molecule, and so it's not straight statistics, it has something to do with shape, it has something to do with availability, and it's more complicated. Who knows? And then there's another question that I think you should ask yourself, if you're feeling it, and that is, once we've done this reaction for a while, the amount of ethane in the flask is going to be going down, and the amount of chloroethane in the flask is going to be going up. And so is this chlorine radical able to bump into this and make a dichloroethane? And the answer is heck yes. If you left it in there for a long time, you could make as many chlorines on there as you were willing to wait for. So this reaction, question-wise, is not your biggest problem. But like experimentally, the issue is that it's not very selective. You get a lot of products. So we, at least 70% of the time, are just going to be like, yeah, do free radical substitution and write the overall reaction, and assume you get the product you want. 18% of the time, we're going to be asked to write the mechanism. And 2% of the time, they're going to ask you something about dichlorinating. And so you're going to have to recognize that you could just do this again. I think I can find one question in 12 years where they refer to the fact that you can make a dichloro. So this is not a common thing. This is just an idea for you right now. Most of the reactions we look at are specific, targeted, fantastic reactions that make just what we want. When Moheb becomes a drug designer in all of the good ways and none of the bad ones, he needs to be really clear of what he's making, right? Like, you do not want to ingest things that have the wrong stereochemistry. That's why we had birth deformities in the 60s and 70s. They made thalidomide the wrong way. People who took that for morning sickness had babies that had like limbs form wrong. It is a stereochemistry mistake. Like, they did the synthesis, but it wasn't specific enough. If you think about how big and complicated drugs are, like, again, all of the good ones and not what you're thinking, like, it's really important that we make the right thing. And so a reaction like this comes with a shortcoming that we're not very good at knowing what we're going to make. And so here we would have to learn how to separate the products.
Well, at least we've moved on from using radium in our drugs.
Things are always getting better. So what you're going to try to do is you're going to try to write the 4 steps. That's going to be 1 initiation, 2 propagation, and 1 termination for the reaction of butane with bromine. No, I'm asked for practice. Right now it seems too easy. What came out of nowhere?
Like, it's just a new chlorine being added in. That's what I'm making sure. There.
This chlorine?
No, but. Yeah.
Yeah, because we have chlorine in, like, chlorine's one of our reactants.
Yeah.
So our 2 reactants are this one and this one, so they're what I have.
Yeah, I was just wondering where that CO, like the HCl went, and then the chlorine came in. They're just moving around and they're getting fine.
So see if you can write that down. Because I just told you that you have almost no control over which products you make, so I thought that there's going to be like panic, which product do I have to make, so I just chose for you. If it was the wrong choice, Rami, just tell me what products you want to make. Butane seems awfully big and kind of disgusting.
I thought if there was like something specific about it.
Just because we do have choices and because you could argue this was methylpropane, that would have been kind of a pain in my ass. I said it was butane, but then I wrote down something that was less specific, so I was just trying to do you a solid. Remove a little bit of ambiguity. So if I wanted to do better, I would write a condensed structural formula for this, and perhaps one for this.
Is this also UV?
You better put in that UV or you don't get no mark. I didn't put it in, you know, just to say that sentence, right? Every time. Are you done yet? I feel like I would do better if I knew what shape this was gonna make. Can't give it to you without knowing. vote now. Who's gonna write me the first step? Go, Remy. Vite moi, vite moi. Allons-y. Quickly, quickly, let's go. Is right ready? Okay, does Remy have to do the arrows to get marks? No, she does not. They are optional. I envision that most of you will not, but I also think it makes sense where the electrons are going if you see them once. So that's why we're writing it again. So Remy has correctly shown you that in the presence of UV light, we can homolytically cleave a bromine molecule into two bromine dots. So that step is referred to as initiation, so I'm going to write an I there just so you remember. Who's going to do the first step of propagation? Let's go, DT. Amarachi, you're going to do the second one. One of them, she's right, the other one. I think the black pens work better than the others, but. Okay, this is the shape it makes, everyone. Retain the shape. I thought I was gonna make a giant triangle. It's a parallelogram. Like I have a practice activity. No, that's dominoes. They just make a line. This is about radical substitution. That's about all sorts of things, but more functional groupy. Okay, everyone's gonna look away. No one saw that. Okay, so Aditi has come up with the second step. The bromine radical has attacked the butane. The bromine abstracted a hydrogen. Are we ready to make 2 bromobutane? Why not, Archie?
We need to attach something.
Okay, we need another step to do it, but I think there's a problem before the second step. No.
There
We
you go.
can, we just need to think about where to put the radical. So the reason I chose 2 was 1, to stop the paralysis by analysis of what am I gonna make. But if you want the bromine to go to carbon 2, you have to take the hydrogen from carbon 2.
So you have to show that on the.
I mean, she drew it out. So yeah, she better show that. I don't think this is a reasonable IB problem still, but I think it's important for all of the things that are coming over the next weeks, that you just have to think about where it's going. The other thing that I'm gonna pick on her for that's also extra, she didn't have to draw the arrows, but she drew it. When you draw the arrows, you see how this beautiful arrow is going from where the electron was to where the electron will be? Do you see how this offensive arrow is going from a hydrogen atom to where the electron will be? I'm gonna spend more time than you want, not deciding if you're a better artist than I am, because all of you are, but telling you that your arrows have to originate at the line. And that's the question you would have asked me tomorrow, so I thought it was just good to leave it there. So the arrow is always gonna go from where the electron was to where the electron is going. And we need to be super clear and careful about that, especially those of you with penmanship problemos. Made that word up. It must be masculine in French too, and Spanish. Los or los? So in French, the word looks painfully feminine. They've gone out of their way to make me think problem is a feminine word by the way they write it, but it is masculine.
There's so many words like that, it makes me so easy.
So I just wondered if in Spanish it was the same as problema, but somehow it's masculine.
Yeah, it's masculine.
Excellent.
So your Tina said it's because men are the problem.
Yeah, exactly.
Oh.
Men are the problem.
Okay,
And
Amarachi,
in French.
step dose. I don't know.
Yeah,
And I know it's un problema because we're not supposed to say una problema.
so basically in Spanish, all words not that end with ma, pa, and ta, they're all masculine, even though they end in a.
Oh, there we go, okay.
Say that again.
All words that end with ma, pa, and ta are masculine. T-A. Those are all masculine.
Can you not use your American accent when you do this? Can you not say like ma instead of like ma, pa, and ta?
Did I say ma, pa, and ta? You said ma, pa, and ta.
No, you're like putting some flair on there so we're not hearing the consonant. So like, can you spell that, sweet?
It's M-A-P-A-N-T-A.
Ma, pa, and ta.
You guys never learned this? This was like the first thing when we got into 6th grade in my old school at Audi. They were like, all these words.
But agua is.
No, they all have ba and da. But they're
Yeah, but agua isn't any of those.
Agua is just a word. No, the reason why is because we can't have ba poet,
Yeah.
because it would be A and A, it doesn't.
And you have the whole problem with neuter.
Sailor is because the C is a woman.
Like the little girl, that's Lena.
Such a pickle.
It's last. It switches.
But you have to say un problema.
Yeah.
Mention, there we go, mention.
So wait, why do people name like boats and
Yes,
cars
das
like
Mention. Girls are neuter.
Go German.
Oh, his degree is in German. Y'all can, talk on the football field about their spiel.
Yeah. That's Coach White. What would it be? What is it? Oh, what would it be?
What are you trying to say?
Coach White on the football team, he always is asking them to call the defense that he is showing. And he's always saying, call it, call it. And so, trying to think of the correct word.
Lapel, lapel. No?
Now I'm gonna be. I need to. What is the right?
Is that not to call in Spanish? Llamar?
Yeah, so if you're like me amo is my name. Like,
No, it is not. It's I call myself.
Yeah.
So he's trying to say call it.
Yeah.
So I came up with apele, because that's how we say that in French. And then I came up with me llamo, so I said llamar.
Yeah.
And now you're saying that's how we say my name, but I'm trying to say Paul.
Call, yeah, no. No, you said me amo.
Yeah, because I was like, je m'appelle,
Yeah.
me llamo, and then I said like, llamar. I was trying to think of an infinitive.
But I put it as a call.
Yes.
Yeah, so look, I call myself.
Yes.
Yeah.
That was something, you've gone through the whole thought process in my head. Thank you for sharing.
You'd be like, Rufinus, Rufinus, Rufinus.
Enrufen means like to call on the phone. The word you're looking for is nennen.
Nennen? Oh, yeah.
My favorite part of
Well, could
German
be
is
like-
essen and fressen.
Ich nenne, du nennst.
Essen is to
Would it
eat, but
be-
fressen is how animals eat.
Oh, I only.
They have like a different word for eating, and so if you've ever watched my boy put down food, like it defines fressen.
Call
Okay.
sign.
I thought it was like one
So.
because it is a one.
Rainy.
So the bromine that's being added to the radical butane, that's different, right?
The bromine will be on the single carbon.
Oh my God, oh, that's supposed to be on the same.
Yeah.
Just change it. Because it's too
Can we start calling Coach White Herr Weiss?
Oh, right,
Herr
right.
Weiss.
Herr Weiss.
So the bromine that's in part 2, that's different, right? No, in the first part. Yeah. That's
Different. It's a new molecule. So remember, I have two reactants here. So the two things I have a lot of are this and this.
Yeah.
During the course of propagation, we make a little bromine radical, we make a little butyl radical.
So then at the end, you'll have two bromine radicals. Okay.
We have,
Okay.
so when I add the reactions to show you this, the overall, I only look at propagation. Because I'm gonna suck up any of the extra bromine radicals that I think you're bothered by with termination.
Yeah, that's what I'm saying. So at termination, the extra bromine radicals can be used as big bromine.
Sure.
Okay, thank you, thank you.
Who's doing my last step? Who's doing termination?
I don't think I do
Let's go, Bert. You can do it on the right board or the bottom, depending on the relative size you'd like to enjoy.
So you don't need more radicals.
No moss.
Yes.
Hater.
Yeah.
Dr. Hennessy,
Yep.
for the second step of propagation,
Yep.
can you draw the arrows, please?
Sure.
Dots, two spots. No, from dots, two spots.
I need the arrows.
It's from dots, two spots. Dots to spots, man.
It's essentially like moving all the free radicals and like putting it back together. Where are you gonna? It's the first free bromation bond is the other molecule. The second one you want to do is science. There's only like if you mention like the intermediate, it's not what it works about.
So I don't do this 100%. So it's like I have bromine in the container and I flip on a light and some of the bromine breaks apart into bromine radicals. Not all of it. There's still a lot of bromine because I'm going to need it.
They were doing that.
The bromine radicals, they can go do this chemistry. They can be in the chain that's going to make this radical propagation happen. The bromine molecules are there to provide new bromines to both make radicals and to make the bromobutane.
So termination is just removing all the free radicals.
Yes, it's any two radicals that die by turning into a molecule.
When you write this like on a test, would you draw it? Would you put the formula? Would you like do the little dash and no hydrogen? Like, I don't know what I would write.
Just be 2 ER with the electron radical, arrow, ER.
That'd be fine. So for this one and this one, I would probably write more or less what you see on the board. Again, the arrows are optional, you can put them in or not at your will. For the middle one, because I forced you to choose the 2-bromo, you would have to draw it out, so they would have to give you an open box to draw it out, because you have to show me that you understand that we're making the radical at that 2 position. But generally speaking, I think that the condensed structure could do that if you wanted to write it on a line. And so if I wanted to show this intermediate, I would do something like that. I don't get to use multiple colored pens, but I would try to show that I knew where the dot was. So that would be a way of writing it on a line, but still showing some location things. So I think condensed structures are probably how I would have approached this if I had a lined box.
So, I think question was, we're gonna have to do this already, you think?
We are going to draw a lot of mechanisms, and so there are many IB questions about mechanisms, but there are few IB questions about this mechanism being drawn. So the skill that you are using today is one that we will use a lot of, but the example is a poor one. It's just this is the only mechanism in SL. All of the other mechanisms, like they give you the reactants and the products in SL, but they don't draw the arrows until HL. And so that's why this one's in sort of a weird place. So you can draw them or not. The HL kids would benefit from it, the SL kids would not.
Are they thinking about putting the dot before or after?
It does not matter if the dot is before or after. They frequently will say in the mark scheme that the dot is not required, but I don't know how we all see this as free radical if you're not showing some dots. So as I was saying, in Karthika internalized, I would really like to see that dot on your page, so in my mark scheme, it's not optional.
Those red arrows, where's it going? It's going down.
You know, it's going back.
Here, would you you like me to, I don't know, I was asked to draw this and I was, like, I could draw it like that if that would help you. Like, I'm trying to make a bond between this carbon and this bromine. So this electron and this electron are making the bond.
Are there any rules on where the bromine is gonna go when you're drawing it? If it's not specified?
Okay, so does this seem less awful than you thought it was gonna be?
I'm not sure yet.
Would you like a quiz on this? I have one.
Yes!
Well, if it's like this, it's okay, but if it gets more complicated,
Open
I'll
note
cry.
quiz?
It is totally like this.
Open note quiz for 100 points?
Okay.
Would you like to add your grade?
I mean, they started really good and then they like stopped being really, really good, so I decided to stop handing it back in real time. Like, I can't grade 15 of them in real time, so I wasn't gonna be able to do it.
Steps for
Okay, so you have now done the first thing. You've taken an alkyl halide or a haloalkane into your group of things you can make. And so if we could connect the haloalkanes to the alcohols, you could take an alkane and turn it into a ketone.
It's a process.
That's gonna be great. So you guys drew 2-bromobutane. We use the terminology primary, secondary, and tertiary for haloalkanes as well. Is 2-bromobutane primary, secondary, or tertiary?
2-bromo,
So just like with the alcohols, what I'm gonna do is I'm gonna circle the carbon that's attached to the halogen. Then I'm gonna count the carbons that are directly attached to it. I'm gonna tell you this is a secondary haloalkane. Good? So the number of carbons attached to the carbon that has the halogen determines that this is a secondary haloalkane or bromoalkane or whatever. Could you draw a primary haloalkane with the same structural formula?
Yes.
With the same molecular formula? Just move it to the end. Okay, that would be a primary guy. Could we get a tertiary guy out of this?
Actually, no, you
So same molecular formula, but I would have to branch. So if I made that molecule, do you agree he's a tertiary bromoalkane? So what a lovely place to start. We're gonna learn how to take primary, secondary, and tertiary haloalkanes and turn them into alcohols. Overall, the formula is really easy. We're gonna take a haloalkane. R means something organic. And we are gonna add a halogen. A warm aqueous solution of sodium hydroxide. Warm aqueous sodium hydroxide.
Wait, so what are we doing right now? What is
You are writing down a reaction. The reactant is any haloalkane and warm aqueous sodium hydroxide. The product will be an alcohol and that halide. That is the reaction we're going to be talking about next time. It's just going to be the pathway of taking what you worked so hard to make today and turning it into an alcohol. That's all. That's just where we're going.
Let's go, Amarachi. It's math time.